Hello, and welcome to your Week 8 lecture video. Since Monday is a holiday, well, Canada Day was actually on Saturday, but in recognition of Canada Day, we got the stat holiday on the Monday, is what I'm trying to say. Since Monday's the holiday, we are missing our lecture class this week, so I'm recording a video to cover the content so we stay on track. I hope you all had a safe, happy, relaxing reading week, and you're ready for the second half of the semester. Today we're going to look at IPv6 addressing. 2 weeks ago we looked at IPv4, and next week we're going to look at how to subnet an IPv6 address. So we're not doing any subnetting with it today, we're just looking at the addressing. So we're going to look at all this stuff here. And a bit more. So IPv6 came about because there were some issues with IPv4. The main one is that IPv4 is running out of addresses. In fact, they're out, right? We're out of IPv4 addresses. Now, what does that mean? Does that mean you can't get a public IPv4 address from anywhere? No, you can absolutely get IPv4 public addresses. But you cannot get them from any of the registrars. You can't go to a RIN or LACNIC or RIPE or APNIC or AFRINIC and acquire an IPv4 address space because they don't have any more to sell you. You can get them from companies who have transitioned a bunch of things to IPv6 and are offloading their IPv4 extra space that they bought. So IPv6 is the successor to IPv4. We've run out of IPv4 addresses. And when they were developing IPv6, and you're probably thinking, what happened to 5? Can they not count? I don't know. But when they were developing for IPv6, they tried to fix a bunch of limitations and issues with IPv4. So we're going to look at that. Now, we did have some measures to extend the life of IPv4 far beyond when it would have expired, like NAT, right? But with the IoT and adoptions in the cloud, or adoption of the cloud, yeah, everything moving to the cloud, right? That's really driven a lot of this. Now, does that mean that IPv4 is totally useless and you shouldn't learn it? No. IPv4 and IPv6 are going to coexist for a long time. The transition is going to take quite a long time. Now, one of the big drawbacks between IPv4 and IPv6, and one of the things making that transition take a while, is they're not compatible. But the IETF has created some tools and protocols to help network admins migrate their networks to IPv6. So we can do things like dual stack, meaning every device has IPv4 and IPv6 at the same time, and that's how most things run. I'm sure if you look at your home router at home, for example, your public IP address, you've got an IPv4 and an IPv6 address. And internally, too, you probably have IPv4 and IPv6 addresses within your own internal network. Another technique that they created was tunneling. So you can transport an IPv6 packet over an IPv4 network. So that IPv6 packet is encapsulated inside a second packet, an IPv4 packet, which then gets encapsulated inside a frame. And they also came out with NAT64, which is NAT for IPv6, and it allows devices with IPv6 addresses to communicate with devices with IPv4 addresses using translation similar to NAT for IPv4. It's just for IPv6. But these are transitioning tools, right? The goal is to move everything to native IPv6 and drop IPv4. And I don't know if we're ever going to reach that goal, honestly. We'll see. It's going to take some time and some work. So I mentioned on one of the previous slides, IPv6 addresses is a much IPv6 addresses are much bigger, and they are. If you remember IPv4 addresses, they're 32 bits in length, and they're written in a dotted decimal notation that we're all familiar with. IPv6 addresses are 128 bits in length, and they're written in hexadecimal instead. Now they're not case sensitive. You can write the letters in hex in either uppercase or lowercase. That's totally fine. And the preferred format is writing it with each hextet or grouping of hex values separated by a colon. Our hextet is the unofficial term that we're being used, but it seems to be catching on, so that's what we're calling them. Here's some example IPv4 addresses in that preferred format. So we've got two examples of IPv6 addresses in their preferred format. You see they begin with 2001, 0, db8, 000. We'll get into the rest of this later, right? But they're really long. We see a lot of lengthy stuff there. In fact, like 4 zeros seems... nobody's going to remember this, right? It's hard enough to remember 192.168.0.1 or something like that. So we've got a couple rules that helps us reduce the length of an IPv6 address, and a computer will re-expand this to its proper form. Sorry, I'm getting messages on Teams. I don't know if you can hear that or not. The first rule is any leading zero can just be omitted because they're assumed, right? Just like anytime we represent binary numbers, we just drop the leading zeros, right? So you can see that that reduces our address significantly. And then the second rule, anywhere where you have a contiguous string of zeros once in the address, you can actually just collapse it to a double colon. So we can take all of these zeros here, including the one in this hextet here, and just, boom, it's double colon. So by implementing those two rules, look how much shorter our address is. That looks like something you might actually remember. So, hopefully that makes sense. I would ask you, but it's a video, so I can't really. We're going to look at different address types and how addresses are formatted, aside from the fact that they're a bunch of hex sets that we just looked at. There's three different types. Unicast, which uniquely identifies an interface on an IPv6 enabled device. Multicast, which is used to send a single IPv6 packet to multiple destinations. And Anycast. These are IPv6 addresses that they're unicast addresses, but they're assigned to multiple devices. So a packet that's sent to an Anycast address is routed to the nearest device that has that address. Kinda like a broadcast, but also not a broadcast. Unlike IPv4, you notice there is no broadcast. There is no broadcast address at all with IPv6, but there is an all nodes multicast address, which gives you a similar result. It's kind of handy. So with IPv4, we've seen addresses represented in the CIDR notation with the slash, right? With IPv6, we do pretty much the same thing, only we call it the prefix length, which is why we're calling that prefix length in IPv4 now. That's where it came from. It came from IPv6. The prefix length can technically be anywhere between 0 and 128, but it's recommended to keep it as a /64, so you can use a whole bunch of things like stateless address auto configuration, which we're going to look at in a little bit. So if you keep it as a /64, that first half of the address, that's unique to the network, and that second half of the address, that's unique to the host, or the interface ID, right? Same idea. Network and host, that's your division. Now, unlike IPv4 addresses, which can only have a single address, IPv6 devices have two unique addresses usually. A global unicast address, or GUA, it's like a public IPv4 address. They're globally unique, they're routable on the internet. And a link local address. This is required for every IPv6 enabled device. It's used to communicate with other devices on the same local link. They're not routable, and they're confined to a single link. So there's all kinds of stuff. Some other useful addresses in here that outside of those are loopback, which is :1/128. And notice unspecified is exactly the same thing. There's unique local addresses, and then you can actually have embedded IPv4 in here as well. Now, the unique local address, which is the range FC00:7 to FDFF:7, they work kind of like the IPv4 addresses defined in RFC 1918, but they're a bit different, a little bit different. Unique local addresses are used for local addressing within a site or between a limited number of sites. They can be used for devices that will never need to access another network, and they're not globally routable, so they can't be translated to a global IPv6 address. So they're similar to 1918, but not like 1918, right? A lot of companies use private addresses internally on their servers, and then will NAT them at their gateway to kind of hide their network. It gives you a little bit more security. Was never the intention of with these unique local addresses, so you don't really do that with them. Global unicast addresses, these are globally unique, and they're routable on the internet. We're currently only using an eighth of the total address space, which ranges from 001 or 2000:3, right? The first 3 bits. Sorry, 001. That's the first 3 bits in binary. So we're not using that much at all, which is a good thing. We've got lots of room for expansion. In theory, we should never run out, but we should keep in mind that we once said that about IPv4. And look where we ended up. So never be too confident that you're going to be completely future-proof. We might need an IPv7 or an IPv8 or whatever it happens to be down the road. So within that global unicast or global unique address, global unicast address, GUA, I can never remember the U. It's broken up into a particular structure. There's a global routing prefix. So that's the network portion of the address that's assigned by the provider, like an ISP. The global routing prefix will vary depending on the ISP. Within there's also a subnet ID. So unlike IPv4, with IPv6, there's only one hextet that you can subnet in. That's it. IPv4, you could subnet kind of wherever you want it, right? Within reason. IPv6, you can't do that. So that subnet ID, that's used by an organization to identify their individual subnets. It makes it a little bit easier. But also, there's more bits in there, so in some ways it's a little more complicated. And then, of course, you've got the interface portion, which is just like the host portion of the address in IPv4. And you should keep everything as /64, which I've already mentioned, right? And another weird thing here. Unlike IPv4, IPv6 actually lets you use the all zeros and the all ones host addresses on devices. The all zeros is reserved as a subnet router, anycast address. That one should only be assigned to routers. But since there's no broadcast, we don't need to reserve that broadcast IP, right? Isn't that weird? Now, link local addresses I mentioned are required as well, right? They allow your device to communicate with other IPv6 enabled devices on the same local link, hence link local, right? Only on the local subnet. Packets with a source or destination of a link local address can't be routed on the internet, and every IPv6 enabled network interface has to have one of these. If it's not manually configured on the interface, the device will automatically create one when you give it a global unicast address. or any other type of address. All IPv6 link local addresses begin with FE80 double colon. Now let's look at our global unicast addresses and link local static address actual configuration. How do you do it? So most IPv6 configuration and verification commands in iOS are just like IPv4. The only difference is, instead of using IP, use IPv6. That's it. So to assign an IPv6 address to an interface, we, from global configuration mode, specify the interface we want to configure and go into interface configuration mode. So in this case, interface gigabit 000, IPv6 address, the address and the prefix. So you have your address there and the prefix. Note, you don't need, remember how we had the address and subnet mask separately? Well, we can just represent it as the prefix with IPv6. So that's a little bit better. And then, of course, you have to bring your interface up by issuing the no shutdown command, which you guys should be familiar with by now. In Windows, manually configuring them is pretty much the same as doing it in IPv4. So we go into our IPv6 settings. We say use the following address. We stick in our address. We stick in our prefix length and our default gateway. And if you want DNS servers, you stick them in there and you say OK. Now, here's a note. When you're using DHCP-v6 or Slack, the link local address will automatically be specified as the default gateway. So that's kind of handy. Means you don't have to worry about forgetting that. To configure a link local address in Cisco iOS, it's pretty much the same as configuring an IPv6 address, except you're using an IP in that link local range, so it begins with FE80. And at the end you include the keyword link local. There you go. The same link local can be configured on each link as long as it's unique to that link. So you could use FE80 double colon 1 colon 1 and FE80 double colon 1 double colon 2 on every single link between devices. Might get a bit confusing, but you could technically do it. You should probably do a different one, right? Now, dynamic addressing for IPv6 works in an interesting way. I say interesting. It's just different. So devices obtain their global global unicast addressing dynamically using IPv6 or ICMP v6. Which, wait a minute, we use that for ping, don't we? No, we use that for this too. There's two different messages that can be sent out for this. Router solicitation messages. These are sent out by host devices to discover routers. And router advertisement messages. These are sent by routers to inform hosts how to obtain their IPv6 GUA portion of the address or portion of the address, and provide other information too that's useful, like the network prefix and its length, the default gateway address, any DNS information, any domain name information, all kinds of useful stuff. Now that router advertisement message can provide three methods for configuring an IPv6 global unicast address. Slack, stateless address auto configuration, Slack with a stateless DHCP-v6 server, or a stateful DHCP-v6 server, which works basically like DHCP in IPv4, but also a little bit different because there's no broadcast. So method 1. Slack allows the device to configure its global unicast address without requiring a DHCP server at all, which is kind of cool. You technically don't need one. It eliminates the need for that. Devices will obtain all the necessary information to configure their address from that ICMP version 6 router advertisement message that's sent by the local router. In there, the router advertisement provides a prefix, and devices then use either EUI64 or random to generate their interface portion, depending on the operating system you're using. So in this case, the router advertisement message, you see it gave the provided the prefix and the prefix length, and then the device generates the rest of this. Now, we could use this in conjunction with a stateless DHCPv6 server. So the router advertisement will instruct the device to create its own IPv6 global unicast address, just like we just did. The link local address on the router, which is the source address in the router advertisement, that gets used as the default gateway for the client, and the router, through this router advertisement message, will direct the client to contact a stateless DHCPv6 server to obtain other information like DNS server addresses and domain names. So that's kind of handy. It's taking some additional load off of the DHCP6 server by having it configure its own address. Or it could use a stateful DHCPv6 server, right? So the router advertisement tells the device to use a stateful DHCPv6 only. It works kind of like DHCP for IPv4. A device can automatically receive the global unicast address and its length, and the addresses for DNS servers, that all comes from the DHCP server. So this works the following way. The router suggests the devices to use the router's link local address, which is its source address for the default gateway, and then everything else comes from the DHCP server. So the only thing the DHCP server doesn't provide is the default gateway. That's the main difference. Now, while we're dealing with Slack, stateless address auto configuration, it could be done in one of two ways. EUI64 or random, depending on the operating system you're using. Using the EUI64, that's a process defined by the IEEE, and it actually stands for Extended Unique Identifier, or Modified EUI64. That first, it's a 16-bit value of FFFE is inserted into the middle of the client's 48-bit MAC address. And then the 7th bit is reversed from a binary 0 to a 1. So this way you get a unique address, right? Because all NICs should be unique. We just take the MAC address and use that to calculate the information. Some people don't like this because you can see the MAC address in it. It is what it is. Alternatively, you could use the random generated ID. This depends on the operating system. Windows has been using this ever since Windows Vista. So what they do is they create a random client portion of the address or interface portion of the address instead of using the EUI64. And because it's random, they have to have some mechanism of resolving whether it's unique or not. So it sends out it uses a process known as DAD, Duplicate Address Detection. It's kind of like ARP. It sends an ARP address for its own, or ARP request, sort of, for its own address. And if it doesn't get a reply, it knows it's unique. If it does get a reply, then it throws it away and generates a new one. Hopefully that makes sense. I would pause for questions, but this is a video, so pause and write stuff down and ask in class if we need. Now, dynamic addresses. Well, they're useful, right? Because all IPv6 interfaces have to have an IPv6 link local address. And just like your global unicast addresses, these can be configured dynamically. So here's showing how this is done using FE80 /10 as the prefix. And then the device either uses EUI64 or the randomly generated 64-bit number to generate the rest. So Windows, here we go. they use the same process. They're going to use the random with dad. So here's our random. I guess they could use the EUI64 as well, but they tend to use the random. There's an example of both. Routers, however, they totally use, Cisco routers use EUI64, and Linux as well uses EUI64, I'm pretty sure. So here we go. We've got our hardware address there, and we see FFFE is inserted into the middle of the address, and then that 0 is flipped to a 1, so we get a unique address. Yeah, there we go. So this one begins with 70. That one's actually 72. So we're using just the show commands here. A note about using the show commands for IPv6, you have to specify IPv6 in the command. So show IP interface brief, the IPv6 equivalent is show IPv6 interface brief, right? There's verifying it, which we just kind of did. Multicast addresses. There's a couple different types of multicast addresses that are used. Because, keep in mind, there's no broadcast addresses, right? Multicast addresses in IPv6 have the prefix FF00/10, or /8, and there's two types, well-known and solicit node. Multicast addresses can only be the destination address. They can never be the source. Well-known addresses, well-known IPv6 multicast addresses, those are assigned and reserved for certain types of devices. Routers, and also not routers. So one is the all nodes multicast group, and the FF02:1. So that's a group that all IPv6 enabled devices join. And a packet sent to that group is received and processed by every interface on that link or network. So it's kind of like a broadcast. And then there's the all routers multicast group. So this is a multicast group just for routers, and routers become members when they're enabled with an IPv6, as an IPv6 router by issuing IPv6 unicast routing in global configuration mode. Then there's the solicit node IPv6 multicast address. So this is similar to the all nodes multicast address, and it's mapped to a special Ethernet multicast address. The NIC can filter the frame by examining the destination MAC address without sending it to the IPv6 process to see if the device is intended as the target. So it's a kind of useful thing. And next we technically get into subnetting, which we're going to look at next week. So I'm just going to ignore it because the slides we look at next week are this, but in better detail. So I hope you all had a safe and happy weekend. It's a pretty quick lecture this week, right? And Friday we're going to be looking at IPv6 addresses. So take care, be safe, have a good week. Bye for now. Thanks for watching.